The same principles apply when combining atomic orbitals from two different atoms as applied when the atoms are identical. That is, number 1, only atomic orbitals of about the same energy can combine effectively. Number 2, they should have the maximum overlap. Number 3, they must have the same symmetry. Since the two atoms are different, the energies of their atomic orbitals are slightly different. The problem is that in many cases, the order of MO energy levels is not known with certainty. Thus, we will consider first some examples where the two different atoms are close to each other in the periodic table, and consequently it is reasonable to assume that the order of energies for the molecular orbitals are the same as for homonuclear molecules. In case of carbon monoxide molecule, the carbon atom has 2 plus 4, that is 6 electrons, and the oxygen atom has 2 plus 6, that is 8 electrons. So, the carbon monoxide molecule contains 14 electrons. In this case, we are rather less certain of the order of energies of the molecular orbitals, since they are different for carbon and oxygen. Assume the order is the same as for light atoms like carbon. We get the molecular orbital energy level diagram, and the electronic configuration of molecular orbitals of carbon monoxide is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2py2, pi 2pz2, sigma 2px2. The inner shell is non-bonding, and the bonding and antibonding 2s orbitals cancel, leaving 1 sigma and 2 pi bonds, and thus a bond order of 3. Alternatively, the bond order may be calculated using the formula bonding minus antibonding divided by 2, that is 10 minus 4 divided by 2 equals to 3. This simple MO diagram is not adequate, since if carbon monoxide is ionized to give CO plus by removal of one electron from the sigma 2px orbital, then the bond order should be reduced to 2.5 and the bond length increased. In fact, the bond length of carbon monoxide is 1.128 angstrom, and in carbon monoxide plus ion it is 1.115 angstrom. Thus, the bond length decreases when we expected it to increase, and it indicates that the electron must have been removed from an antibonding orbital. The problem remains if we assume the order of energy for the MOs is the same as for atoms heavier than carbon, since this only reverses the position of the sigma 2px and the pi 2py and pi 2pz molecular orbitals. The most likely explanation of the bond shortening when carbon monoxide is changed to CO plus is that the sigma 2s and sigma star 2s molecular orbitals differ in energy more than in shown in the diagram. This means that they are wider apart, and the sigma star 2s MO is higher in energy than the sigma 2px, pi 2py and pi 2pz molecular orbitals. This illustrates very plainly that the order of MO energy levels for simple homonuclear diatomic molecules used above is not automatically applicable when two different types of atoms are bonded together, and it is certainly incorrect in this particular heteronuclear case. Now let us consider a MO diagram of nitric oxide molecule. The nitrogen atom has 2 plus 5 equals to 7 electrons, and the oxygen atom has 2 plus 6 equals to 8 electrons, making 15 electrons in the molecule. The order of energy levels of the various MOs are the same as for homonuclear diatomic molecules heavier than C2. So the arrangement is sigma 1 is 2, sigma star 1 is 2, sigma 2 is 2, sigma star 2 is 2, sigma 2 px2, pi 2 py2, pi 2 pz2, then pi star 2 py1, pi star 2 pz0. The inner shell is non-bonding. The bonding and antibonding to s orbitals cancel, and a sigma bond is formed by the field sigma 2 px2 orbital. A pi bond is formed by the field pi 2pz2 orbital. The half field pi star 2py1 half cancels the field pi 2py2 orbital, thus giving half a bond. The bond order is thus 2.5, that is in between a double and a triple bond. Alternatively, the bond order may be worked out as bonding minus antibonding divided by 2. That is 10 minus 5 equals by 2 equals to 2.5. The molecule is paramagnetic since it contains an unpaired electron. In NO, there is a significant difference of about 250 kJ per mole in the energy of the atomic orbitals involved, so that combination of atomic orbitals to give molecular orbitals is less effective than in O2 or N2. The bonds are therefore weaker than might be expected. Apart from this, the molecular orbital pattern is similar to that for homonuclear diatomic molecules. Removal of one electron to make NO plus results in a shorter and stronger bond because the electron is removed from an antibonding orbital, thus increasing the bond order to 3. Now let us consider the molecular orbital diagram of cyanide or CN. The carbon atom has 2 plus 4 equals to 6 electrons, and the nitrogen atom has 2 plus 5 equals to 7 electrons. So the CN molecule contains 13 electrons, and the configuration will be sigma 1 is 2, sigma star 1 is 2, sigma 2 is 2, sigma star 2 is 2, pi 2 py2, pi 2 pz2, and sigma 2 px1. The inner shell is non-bonding, and the bonding and antibonding to s orbitals cancel, leaving 1 sigma and 2 pi bonds, and thus a bond order of 3. Alternatively, the bond order may be calculated using the formula bonding minus antibonding divided by 2, that is 10 minus 3 divided by 2 equals to 3.5. This simple picture is not adequate since Cn is ionized to form Cn minus ion, and the electron is added to a bonding electron and to the bonding molecular orbitals, so the bond order will be increased and the bond length of Cn minus will be less than that of Cn. With heteronuclear atoms, it is not obvious which atomic orbitals should be combined by the LCAO method to form molecular orbitals. In addition, because the energy levels of the atomic orbitals On the two atoms are not identical, some molecular orbitals will contain a bigger contribution from one atomic orbital than the other. This is equivalent to saying that the molecular orbital bulges more towards one atom, or the electrons in the MO spend more time around one atom than the other. Thus, some degree of charge separation, del plus and del minus, occurs, resulting in a dipole. The partial ionic contributions may play a significant part in the bonding. Consider the HF molecule combination between the hydrogen 1s atomic orbital and the fluorine 1s 2s 2p orbitals can be ruled 1s and 2s orbitals can be ruled out because their energies are too low. If overlap occurred between the fluorine 2py and 2pz orbitals, it will be non-bonding because the positive lobe of hydrogen will overlap equally with the positive and negative lobes of the fluorine orbitals. Thus, the only effective overlap is with the fluorine 2px orbital. The combination of hydrogen 1s1 and fluorine 2px1 gives both bonding and antibonding orbitals, and the two electrons occupy the bonding molecular orbitals, leaving the antibonding molecular orbital empty. It is assumed that all the fluorine atomic orbitals except 2px are localized on the fluorine atom and retain their original atomic orbital status, and thus 2s, 2py, 2pz orbitals are regarded as non-bonding ion pairs.